Today, we're going to begin our journey into ray tracing, which is a method used by 3D animators and game designers in order to create really high-quality visual effects. Though we're going to end next week with the ability to create visualizations like these, this week we're going to focus on the prerequisites. And by that I mean we're going to hone in on one particular example of 2D ray tracing and show how ray tracing models physical light, in particular how we can model reflection off a mirror and refraction through a lens. So let's start by talking a little bit about light. Firstly, the white light from this lamp is a composite of all of the colors of the rainbow. We can model the light emanating from the lamp as a nearly infinite number of rays moving in all directions, all of which hit different objects before bouncing back into our eyes to make sense of the world around us. For example, let's look at this mandarin. Here, some of the light rays from various light sources make their way towards the mandarin. The mandarin then absorbs most of the light, but reflects off orange light. That orange light from the mandarin then goes off in a number of different directions, some of which end up in our eye. This is essentially the process we're trying to replicate with ray tracing. Light leaves a light source, bounces around the room, and accrues color from different objects before eventually landing in our eye. When thinking about how to implement this in code, there are a number of important questions to consider. 1. How do we model light propagation? How does light move forward exactly? 2. How does light reflect off of various objects? And 3. What about transparent objects like water or glass? In these cases, we have to talk a little bit about refraction, which again we'll talk about more when we get there. For the first point, we'll talk about two different methods. One is time-stepping light. This is typically used for simulating how light moves through clouds or smoke, anything without a hard edge. And 2, we'll talk about event-driven simulations of light. This is where we mathematically determine when each light ray will interact with another object, resulting in less overall computation. Now, for today, we'll be discussing just time-stepping of light, but we'll be discussing event-driven simulations, which, again, are the more traditional form of ray tracing in homework. As a note, there will be a lecture on Thursday on event-driven simulations with something known as a billiard model, which will also set the stage for subsequent lectures. So, if we're going to time-step light, what would that look like in code? Well, I typically create a struct for the ray itself with the position of the tip of the ray and a direction. Here, I'm notating the direction as just L for light ray. You could name it whatever you want, but that's just what I'm calling it here. Both of these will just be vectors with an XY element inside of them. Now, there's something special about this struct, and that is the mutable tag right here. For the purposes of this conversation, we're just going to say that mutable means that the interior contents of this struct can change with time. That is to say, we can create some sort of function that acts on this ray, and it could change the light's light vector L or its position P. In addition, I keep another metric to help me understand the speed at which the ray is moving. I'm going to call this metric an index of refraction, or IOR in code, but there's a lot of physics hidden in this value that we should probably talk about. Here's the deal. Light is actually really weird. Some of you guys might have heard that in certain cases, light can be treated as a wave, and also that light moves the same speed, regardless of how fast we're moving. Both of those are completely 100% true. But for today's lecture, we're focusing primarily on the area of computer graphics, where we don't really have to deal with the wave-like nature of light, and we assume that really we're not moving too fast with respect to the light itself. Now, for us, the speed of light is 3.0 times 10 to the 8th meters per second, assuming there's nothing around it. If light moves inside of something else, like water for instance, it will be a significant amount slower. How much slower? Well, we know from experiments that it's roughly 1.33 times slower. This means that the speed of light in water times 1.33 will equal 3.0 times 10 to the 8th. We often call that value of how much slower light is in another medium the index of refraction, which is what we used earlier in code. Now, typically this is denoted as n, but we're going to be using IOR for the code in this lecture because n will be used for something else later on. Now, air is a special case. Because it's mostly empty space, its index of refraction is roughly 1, which means the speed of light in air is incredibly close to the value we typically know for light, which again is 3.0 times 10 to the 8th. Now, no matter what medium light is moving through, the relationship between the velocities can always be given by a simple equation. C is going to be equal to 3.0 times 10 to the 8th, which is going to be equal to the index of refraction times the speed in that medium. So, for example, we could have the index of refraction in air times the speed of light in air, and the index of refraction in water times the speed of light in water. We're going to come back to this later, but here I wanted to drill home the point that if we want to move our light rays forward with time, we need to know their current position and the velocity at that position, which can be provided as an index of refraction, as c over n. For now, we can create a simple function that will allow our rays to move forward with time by saying that the new position of each ray will be equal to the old position with its velocity times some small time step. This is the simplest possible form of time stepping, which is an entire field unto itself. Now, as a quick note, I'm making a very small distinction between the speed of light and the velocity of light, and let me clear that up right now. The speed of light is simply how fast it's moving. The velocity is not only how fast it's moving, but also the direction by which it's moving in. That's why in this particular function, I have the direction with the index of refraction value put together, and we assume that light will always be moving 3.0 times 10 to the 8th meters per second, and then be divided by the index, which is why this function works as a simple time-stepping scheme. We will probably be covering some more complicated time-stepping schemes later on in this course, particularly when we talk about climate simulations, but that's a discussion for another day. So now we need to create a main function that creates a bunch of rays of light and moves them forward with time. In addition, we need to create some function, which I'm just going to call propagate, which just calls the step function every time step. Here, I'm going to store all of the values of the rays of light in some large matrix, where each column is an independent ray, each row is a time step, and the depth dimension will simply be the x, y coordinates of our ray. If we're doing 3D, it would be the x, y, and z coordinates. That's why this array is going to be the ray number in one dimension, the n, which is the number of time steps in the other direction, and then the dimension, which in this case is just 2 in that last dimension. This allows me to easily plot it at the end to create this image. It's not much to look at right now, it's just a bunch of rays of light all moving in one direction, but don't worry, it gets a lot better, and we'll talk about how to make it better in subsequent sections. Now that we have light propagation out of the way, we need to implement the concept of a mirror. I'll be honest, most people probably already have an intuitive grasp for how mirrors work. The idea is that light goes from up here, and then it bounces onto me, bounces to the mirror before going into the lens over here. That's exactly what we're going to be replicating in code. If we were to draw this, we would see light hitting the mirror and then bouncing off like so. Of course, to put this into code, we need a more rigorous definition, so let's draw a line right down the center. Also, let's constrain our mirror to be lying horizontally on the table. No matter what ray of light we send onto the mirror, the reflected ray will be moving at the same speed in the x direction, but the opposite speed in the y direction. If the mirror is hung on a wall, the opposite is true. The ray will be moving at the same speed in y, but the opposite speed in x. In both cases, we see that the angle of reflection is always the same angle as it hit the mirror with. This means that as long as we can find that angle, we should be able to find the new reflected direction by first finding the component of the velocity we want to flip, and then subtracting it twice from the appropriate direction. Note here that this argument relies a bit on the projected vector being perpendicularly outward from the mirror. This is why that vector is given a special name, the normal. Okay, it's kind of a weird honor to be called a normal, but it does hold particular importance. Anytime we talk about a normal vector, it's simply a vector pointing directly outward from a surface, which is incredibly important for future calculations. If we only consider horizontal and vertical mirrors, we could write some simple code that does flipping for us. But what about mirrors that are neither horizontal nor vertical? Well, in these cases, we need to figure out the relative alignment of the ray of light and the mirror, and there is a particular vector operation to do that for us, the dot product. This operation conceptually returns the amount of one vector projected onto another, so let's look at a more concrete example. Here, we'll be taking two vectors, A and B. B is aligned in the x direction and acts as the vector 1, 0. If A and B are the same vector, therefore A is also the vector 1, 0, the dot product will return a 1. If they're perpendicular, i.e. A is now 0, 1 instead of 1, 0, it will return 0 for the dot product. As A sweeps between all possible values between the two vectors, we see that the dot product only returns the x component of A. So here, for example, is a ray that is aligned at 45 degrees and therefore has 1 over square root of 2 for the x and y components. The dot product will just return 1 over square root of 2. And again, the reason it does this is that the dot product is basically a projection of A onto B, and because B is only in the x direction, it only returns the x component of A. So what exactly is happening under the hood? Well, the dot product is simply going to be adding the components of each vector that are in the same direction. So the dot product in 2D for vectors A and B is just going to be A dot x times B dot x plus A dot y times B dot y. As an important note here, if B was in some other direction and we performed the same analysis, the dot product would still return the amount of A projected onto B. In fact, the dot product can also be written in terms of trigonometric functions, as the dot product of A and B is going to be equal to the magnitude of A times the magnitude of B cosine theta. This is why we can directly substitute the dot product in for the reflectivity function we created before. So going back to our reflection example, any reflection will simply be whatever the light ray was before, dot minus equals 2, and then the dot product of the ray dot L, and then n, times the normal vector. By multiplying by the normal vector at the end, we'll always find the amount of the light vector being projected in the direction perpendicular to the surface, and then we just subtract it twice to reflect it. Okay. At this point, if we go back to the rays of light from before and put in a tilted mirror, they will all reflect upwards, which is cool. Now on to the final step. For this, we're going to have to describe reflection's beloved cousin, refraction. But before we go there, I do need to do a quick little piece of bookkeeping saying that this particular video is going to change in style for this particular section. The reason for that is twofold. One, I've been up since 3 o'clock in the morning editing this video. It's currently 7, actually close enough to 8 p.m. in the evening. I've been doing nothing but editing all day, and I still have another like 5 hours of editing to do if I use the old style. The other reason is that this upcoming section requires a lot of mathematics, and because of that, it's kind of nice to kind of go at a slower pace so we can get through things one step at a time, hopefully at a pace that you guys will be able to follow maybe a little bit better. So what exactly is refraction? Here's the basic concept. I'm going to create a well of water down here, and I'm going to do the same thing I did before, shooting a single ray of light towards this surface. Now with reflection, you would expect a vector to hop right off like this, but as we all know, that's not exactly how water works. Instead, we see a bending of light as it goes into water towards the normal. That looks something like this. And this is a standard example that we would call refraction. So the obvious question is, why does this happen? There's actually a pretty cool animation of exactly what's happening on Wikipedia. The idea is if we can think of light as a series of waves emanating from a single point, you'll see that as light enters the new medium, it slows down, again because of the index of refraction that we talked about before. When it slows down, the wavefront changes a little bit, causing a bit of refraction. Now again, for the purposes of this lecture, we don't really need to deal with the wave-like nature of light. Really, we just have to deal with the fact that the ray goes in one direction, and then when entering the new medium, it goes in the other direction. So let's start by drawing the equation that we wrote down before. C is going to be equal to 3.0 times 10 to the 8th meters per second, which is going to be equal to the index of refraction in air, let's say, times the speed of light in air, which is going to be equal to the index of refraction in water times the speed of light in water. By rearranging this equation, we can find the following. N of air over N of water is going to be equal to the speed of light in water over the speed of light in air. So now I'm going to erase this up here, and I'm actually going to move this equation up here to the top, because there's a famous equation known as Snell's law, which basically says that the change in refractive index is also related to the change in angle as you enter the new medium. So here we have two different thetas. One will be the theta for water, and the other will be the theta for air. And I'm going to draw them here just for clarity. So this will be the theta incoming for air, and this will be the theta outgoing for water. Now, this is an important equation, so we're going to keep it in mind as we go further. So let's take this equation and let's move it somewhere, shall we? How about down here? So let's say we want to solve for theta water. Well, we know that theta water is going to be equal to the arcsine of the index of refraction in air over the index of refraction of water times the sine of theta in air. This is just a simple reordering of the equation. We also know, looking at these two lines up here, assuming that this is L of air and this is L of water, the L of water is going to be equal to the negative normal, again, that's just the normal going in this direction here, over cosine of theta, water. If you're having trouble conceptualizing this, remember that cosine is just going to be the adjacent over the hypotenuse, right? So cosine of theta, water, is just going to be equal to, again, adjacent, which is going to be the negative normal, over the hypotenuse, which is L. Rearranging this equation, you get this equation down here. So now let's write that down as well over here. So we know L of water is going to be equal to the negative normal over cosine of theta water. In principle, we can plug theta water in here, and it would work just fine. However, in general, we tend to avoid using trigonometric functions in code simply because they're slow. So what we typically want to do is instead use vector notation whenever possible, kind of like what we did before. This is where a lot of the math comes in, so I'm going to draw a little dotted line here. To get started, we can say that the index of refraction of water times the light direction of water is going to be equal to the index of refraction in air times the light direction in air plus the index of refraction in air cosine of theta air minus the index of refraction of water times cosine of theta water times the normal. And I do realize that I'm getting my notations a bit mixed up here. So let me just be clear. Anytime I have a hat on something, I mean specifically the normal. If it doesn't have a hat on it, it means it's not normal, which isn't to say that you're not normal if you're not wearing a hat. All I'm saying is that the hats are normals, the non-hats are index of refractions. This is actually why in code I was using IOR, and in principle I probably should have been doing that here mathematically as well. But, you know, okay, I need to be clear. What is this saying exactly? This right here is a projection of the normal above the surface. So this is a projection onto the normal above. This down here is a projection onto the normal below. And what we're doing here is we're seeing how far the normals have changed, thereby giving us a ratio of how far our angle has shifted. The main issue here is that there are two unknowns. We don't know L of water, but we also don't know cosine theta of water. Even though they're related, we can't use any wishy-washy math to kind of wave them away like a lot of physicists do. But we can actually bring back in Snell's law. Here we know that theta water is equal to this equation in here. So in principle, theta water is not completely unknown. Also, let me put parentheses down here. We also know that sine squared theta plus cosine squared theta is equal to 1. So let's move this down here. And we're going to rewrite this equation to be something slightly different. To say instead that sine of theta water is going to be equal to the n air over n water times sine of theta air. Now this is going to be equal to n of air over n of water times the square root of 1 minus cosine squared of theta air. Now, again, the reason we actually want everything in terms of cosines are again because dot products are defined in terms of cosines. Remember that A dot B is going to be equal to the magnitude of A times the magnitude of B, cosine of theta. And if A and B are normalized and therefore 1, they can be ignored, and therefore A dot B, for the most part, can be assumed just to be cosine of theta. Again though, this is only if A and B are normalized, which just so happens to be the case with our incoming light vector and the normal vector off of the surface of the water. So this means that the cosine of theta water is going to be equal to the square root of 1 minus n of air over n of water times 1 minus cosine squared of theta air, which again will be equal to the dot product of the negative normal dot L. Now, for convenience, we typically call this term C, and we also call the ratio between n air and n water to be equal to R, the ratio. We find that L of water is going to be equal to the ratio times L of air plus the ratio times C minus square root of 1 minus R squared times 1 minus C squared. And so that is the equation that we need to solve. Okay, so what does this look like in code? Well, it looks almost identical to what you would expect. We have C, and then we have D, and then we do Ray.L is equal to the index of refraction times Ray.L plus the index of refraction times C minus square root of D, where D up here acts as this internal term for the parentheses. Now, there's one little trick here that I do need to point out, and that's what's happening here. See, there's something called total internal reflection, or TIR, and let me explain it with this diagram that we have up here. Let's say our light is actually coming towards the surface of the water here, such that the index of refraction on the outside, air, is less than the index of refraction on the inside where it's propagating water. In this case, if you approach at a shallow angle, there's a possibility for it to reflect instead of refract. And this is the concept of total internal reflection that we're dealing with down here. Essentially, if this D value is less than 0, we just return a set of zeros. Then in the code, if we know that the refract function is returning a set of zeros, we're simply going to call the reflect function instead on the incoming ray of light. Okay, there's one last thing we need to talk about, and those are lenses. So lenses are like magnifying glasses and stuff like that. For the purposes of this particular lecture, we're only going to deal with circular or spherical lenses. And the reason we want to do that is because 1, it makes things easier, and 2, I'm kind of running out of time. We're going to talk maybe about more complicated shapes next week if we have time for that. Now, this lens will act pretty much identically to the body of water that we had before. Light will come into the lens and then interact with the lens on the surface boundary. Now, like before, it'll bend towards the surface normal. And then when it leaves, it'll bend back away. Now, if we send a bunch of rays of light towards this lens, they'll all kind of do the same thing, and they'll do a semi-focusing event here on the edge. This is called spherical aberration. And really, the only trick to this is that we have to deal with light when it's inside of the lens as well as when it's outside of the lens. Essentially, what we need to do is we just need to find the direction of the normal. Is light approaching the lens, or is it leaving the lens? So firstly, how exactly do we find the normal vector of a sphere? It's just going to be a normalized function of the ray's position minus the lens's origin, which I'm also going to call P. This means that when you get to the surface of a lens, the normal will always be projected outward. So if we're trying to find a way to determine if the light ray is coming towards the lens or being away from the lens, we can simply do a dot product of the normal from the lens to the light's direction. And if we get a negative from here, we know that the light ray is coming in another direction, and therefore we need to refract out the other way. So putting this all together, I created a bounded box of mirrors, and then I sent a whole bunch of light towards a mirror in order to create a spherical aberration image, which I think turned out pretty cool. And this is hopefully what you guys will be doing for homework, except in an event-based manner. Now, this is still very far from the cool 3D visual effects that you can find online, and don't worry, we'll hopefully get there next week. We still have to add in the third dimension, color, and a whole bunch of recursive tricks in order to make those animations. Now, this week, because we're still focused on the prerequisites, we're going to cover naive parallelism later today, along with event-based modeling with a cool billiard model on Thursday. With all of that at your disposal, you should be able to tackle the homework this week, which will be basically creating the visualization I just made, except with an event-based model. Next week, we'll do full 3D ray tracing, so hopefully I'll see you then. Thanks again for watching, and yeah, I'll see you next time. Bye.